Today, we're going to program. So, and I think today is going to illustrate everything about why I started teaching this class. So I mean that in a serious way, because we're going to program up your Advection Diffusion, which you did for homework 4, and we're going to do it all spectrally. And my hope is, what it illustrates to you more than anything else, is what hopefully you can start seeing is being able to do computation on a whole different level, which is within a 40-minute block. We can basically take some nonlinear complicated PDE, put it all out, get it done, run. Okay, so that's ultimately what this class is all trying to do for you, right? You have a research problem. It used to be you were a little bit paralyzed. Oh, I got to solve this PDE. It's going to take me months to get it all figured all out, or whatever it takes, and it seems like such a big hurdle. Here, we're going to talk 40 minutes. You're solving code. You're getting results. Okay? There's a big shift of what's happened. When I was in grad school, things are different. We didn't quite have all the power that you have today. Okay, so let's talk about spectral implementation. And let's take a generic PDE that might look something like this. Okay, so where L maybe is some kind of operator that has derivative terms. Plus constant, and then N is the rest. Nonlinear terms, non-constant coefficients. And part of what I was basically propose is, in the spectral technique, is say, what we want to do is we want to solve this. And this relates directly to your homework 5, where I give you the spiral waves to solve. You're going to see some super sweet spiral waves on your screen. And if you look at them for a long time, you'll be like, get dizzy and fall over. Okay? But you kind of go like, what's the generic way to solve this? Well, what I want to do is use fast Fourier transforms, so I'm just going to fast Fourier transform everything. And here's what happens with this. Now, you're in the transform domain, and I'm fast Fourier transforming in X, and this becomes just something like this. I now have a differential equation. And I can throw that into OD4-5. Where A of k took care of all this stuff. This is some function of the k wave numbers. Well, I mean, what is A of k? Well, if I Fourier transform LU, well, LU is A, 2 derivatives of x, plus B, 1 derivative of x, plus C times U. And then you say, well, okay, if you Fourier transform that, right, what happens to derivatives? 2 derivatives pull out an ik, and you square them. So it's going to give you a minus ak squared Fourier transform of the function. This will plus ikb Fourier transform plus c Fourier transform u. And then if I put all that together, what I have is u hat multiplying minus ak squared plus ikb plus c. And this is my, what I called A of k. Okay? So there you go. And then you just OD4-5 that. So you're not actually solving the time domain. You're solving for the evolution in the frequency domain. In particular, you are solving now for how do the frequency components change in time. They change like this. Here are the equations. And so this is what you're going to solve for. Yeah?
Assuming the boundary condition is periodic.
That's right.
Okay.
Periodic or far away? For us, far away. Out there, stuff.
So it could be anything.
Going to be 0.
Just say eventually it's 0, and therefore it's going to repeat.
Yeah, in fact, really, anything below 10 to the minus 6 is effectively noise, right? What I mean by that is the following. When I step forward in OD4-5, and I make this comment to you, right, in homework 5, talking about, or actually, I did it in homework 4 about your GMRes and BiCG stab, right? It's like, well, what's the generic accuracy of these things? It's like 10 to the minus 6, right? So 10 to the minus 6 is your generic thing. So like if you're trying to get stuff down, like I want this down to 10 to the minus 10, it's like, wait a minute, every step you take is making a mistake of 10 to the minus 6. So for instance, in your homework, for homework 4, you started picking a spatial discretization of dx, right? You pick a dx, and suppose your dx was 0.1, right? So you take this domain, pick a dx, suppose that dx is 0.1. And in homework 4, we said, hey, you know what, use a second order scheme. So what's the accuracy of this thing? Well, it's this squared. So you're kind of like, you know, something like that in accuracy. And then GMRes and BiCG-stab is an iteration routine, right? And what it's going to do is going to crank out the solution and get it to converge all the way down to 10 minus 6. Right? You're working really hard to get down to 10 minus 6 when every single thing you do has an error of 10 minus 2. 4 orders of magnitude bigger. So why would you make GMRes and BiCG-stab work so hard for something so wrong? You wouldn't. You might say to BiCG-stab or GMRes, you know what, go to 10 minus 3. It's an order below this. Fine. Okay, does that make sense? A little bit, hopefully.
So boundary conditions like 10 to the minus 3, I mean, if you're within...
Yeah, if this is your discretization, what does it mean to get out there and go, oh, is it really small? It's like, yeah, well, whatever. You're making this kind of mistake. So it becomes suspect. In other words, you don't want to overwork at something when you're making a huge mistake over here. I think the Bible says, take the log out of your own eye before you, do you know that saying? Anyway, okay, my dad's a minister, so throw that out there. So I kind of can quote some stuff. But anyway, something like that. So it's the same thing here. Take the log out of the numerical scheme before putting your own log in or something. Anyway, we can make some modifications of that. All right. Okay, so here's what we're going to do today, just to illustrate the awesome power of what you can do. We're going to solve this equation, which you've already done, all spectrally. Okay? So first of all, you already know how to solve this. In homework 4, I said solve that using the FFT. So what you knew about this was, you know, you can solve this by saying you have this relationship that the Fourier transform in x and y is equal to negative we have that result that we developed in class. So that's your fast Poisson solver. You've already done this, right, in MATLAB for your homework. Okay, so now it comes to this part here, which is taking care of this. So let's rewrite this again here. So it's omega t is equal to this. And then over here, minus. Does anybody remember what that looks like? Is it psi of x omega y, or is it? Okay, there we go. And if I bring that minus sign through, then that becomes a minus there and a plus there. Okay? So we're going to solve this, and we're going to Fourier transform it. So now you're going to Fourier transform in x and y, everything. Notice these are nonlinear terms. Well, not nonlinear. They're linear in omega, but psi is related to omega, so they're effectively sort of nonlinear terms. So you're going to this is like your n of u term. You're going to say, I have to compute this, and then Fourier transform that whole thing. When I Fourier transform this, it's going to be that. This is easy. Fourier transform of 2 derivatives in x and 2 derivatives in y. 2 derivatives in x is going to pop out of ik of x squared, which is minus kx squared. 2 derivatives of Fourier transform in y is going to pop out at iky squared. So this thing here becomes negative omega kx squared plus ky squared omega hat plus Fourier transform of all the rest of that stuff. It's nonlinear, so I just have to compute it all and then Fourier transform it. Couple things to note. This is two-dimensional. So it's really convenient to write this like this. Kx squared, ky squared. I know what kx is. It's the kx value is in the x direction, ky is in the y direction. Your computer doesn't know that. You have to teach it this, right? You have to give it a sense of directionality. You have to tell it that there's an X direction, there's a Y direction. Okay? So we're going to go solve it. And notice, though, we are solving everything in the Fourier domain. We are solving for the evolution not of omega, but of the Fourier coefficients of omega. This is the dynamics we're solving for. Okay? Okay. Yeah, this is a, this is a, yeah, perfect. Fourier transform in X and in Y.